So I am Laurent Decreusefond. I am a professor here since a very long time. And this is a joint work with Laurent about invertibility on Poisson space and box processes. Actually, invertibility on Poisson space, and then it ended with some new construction of box process. Super. Alors, c'est original ça. Hein? Bon, écoute, comme ça marche. Bon, ok, je sais pas pourquoi. So if we start at the beginning, what is a point process? A point process is a sequence of points on R+, which are ordered. T1 is strictly less than T2, and so on and so forth. And we have the interarrivals, which is the gap between tk plus 1 and tk. And the number n is the number of arrivals before time t. That means the number of k such that tk is less than t. Standard stuff. And a Poisson point process is when the interarrivals are IID and distributed as an exponential of parameter lambda. So if you want to, it's a very easy algorithm. If you want to simulate a Poisson point process, you start with time t equals 0. You have an empty list, and while t is little t is less than capital T, you draw an exponential, and then you put it that you add to the current time t, and then you to the list A you append the time t, and in the end you get T1, T2, T and T. That means all the arrivals, all the other times before time capital T. Okay. Just to remind something trivial. So these are some four sample paths of a Poisson process. As usual, you have gap somewhere and you have clusters. Strange because you draw things uniformly and you have clusters. This is not the subject. So when to use Poisson process? You use a Poisson process when you want to, when you have a large number of sources, and each source has a small activity rate, and then the product of the two is more or less a constant, around 1 or 10 or whatever. But it doesn't tend to 0 or it doesn't tend to infinity when n is large. So it's the law of rare events. You have a lot of sources, and all the sources are have a very small activity rate. Okay, so that's it. That is well known. What can we do next? The thing which is important for a Poisson process, it has independent and stationary increments. So one way to describe this is to say that the number of arrivals between t and t plus h, the probability that it is greater than 1, at least for h small, that means it is equal to 1, given the path of the process up to time t, is lambda h as something which is neglectable with respect to h, as h goes to 0. Okay, this is the property I will use to describe what I need. Okay, the first question we can ask is, can we have some process where the local intensity, as it is called, depends on t? That means if the arrival rate, mean arrival rate, depends on t. In a Poisson process, the mean arrival rate is constant, equal to lambda. And now we want to have some more freedom in the definition of our process. We want lambda to be able to depend on t. So this is called a non-homogeneous Poisson process, and the way to construct this is you are given lambda. Here you take the first primitive of lambda, which is called A, and you make the time change of n. You take n of at, that is, you accelerate or decelerate the time. And it's relatively easy to show that for the local intensity of NA is indeed lambda t time h plus something which is negligible with respect to h. So this is well-known stuff. Non-homogeneous Poisson process are not so useful, but yeah, just an opinion. And if you look, that means that the cave jump of NA is the image by the inverse of A of the cave jump of N. So the thing here is that I assume that lambda of S is strictly greater than 0 for any S. Otherwise, you may have some difficulties. So that means that A is continuous and strictly increasing. So it's a bijection from R plus onto R plus. So there is no problem with this. So N minus 1 is well defined, and the cave jump for NA is a cave jump, the image by N minus 1. Okay. So far, so good. But now I'm still not satisfied. Now I want a local intensity which depends on the process itself. Okay, I want that the probability to have an arrival between t and t plus h, given the sample path of my point process up to time t, is something which depends on the whole path of y up to time t strictly before time t. I don't include time t in lambda. Okay, so can we construct such a point process which satisfies this this equation? And if you remember what is here, you see that when lambda is deterministic, you want to construct NA as n with a time change here. So the question is, can we do the same thing for something which is random? That means if we mimic exactly what we did for the deterministic A, can we construct a process which satisfies this equation? And the question 0 is, why do we care? Why do we want to construct such a process? The answer is that, you see, this is called a self-excited process because the number of variables after time t depends on the processor itself before time t. And the main example of self-excited process we have is what is called Hawkes process. So what is Hawkes process? Hawkes process have been introduced by Hawkes and Hawkes, Hawkes H-A-W and Hawkes O-A-K. It was at the beginning to modelize seismic activity. That means when you have a first earthquake, the earthquake generates some replicas. And each replica generates itself another replicas. And each replicas of replicas generate replicas. So you have a sort of cascade of replicas, and you want to model the global behavior of all the replicas. You have some other situation in which it is used. It's neuron discharge. A neuron has a potential, and then when its potential is above a given threshold, it discharge. There is a discharge to the potential goes to the basic potential. And when a neuron fires, it increases the potential of his neighboring neurons. And then for so it's you have as many Hawkes processes as you have neurons, and they all excite the others. So it's something. It's a more complex model. I won't talk about it here. So yeah.
You might also for some kind of modelization at work in the past. If say similar traffic, using, for example, functional motion.
Yeah.
Is it something that could be also modeled by this kind of thing, or is it very different?
I don't know what to answer, because I think that Mathieu Rosenbaum had some result where he shows that the limit, in some sense, of this kind of process converge to a fractional volume motion. But I'm not sure. But at the very beginning, it seems different.
When the self-intention is going towards instability, then we find
that the volume fractional motion. In insurance, that means that when you have a company, a telco company which fails, that means it's very likely that some other company of the same domain are going to fail, because the domain is increases and you have some sort of negative excitation. So what is this figure? This picture here? This picture is an order book. So an order book is something where you put, you want to buy some asset. You say, I want to buy this asset at the price here, and I want to buy as many assets as what is indicated here. And the guy which is here say, I want to sell the same asset at the same price, at this price for this quantity. And when they match, you have a transaction. And what has been observed is that when you usually, when you have a buy order which is placed, the next order is usually a sell order. So this can be modeled by the difference of two Hawkes processes, which are mutually exciting. And you have many, many other situations where you can consider Hawkes processes. Okay. Okay, so what's so this is the description I told you about before. Of course, you have to have some condition to have not too many events, otherwise we have an explosion. And everything will. Maybe this is this situation. You mean where when you just are close to that, but
you can say
to one, or at least R0 goes to one. R0 goes to one also. Yeah.
So why call it self-exciting? Because depending on the function that you take, you might just space things and trigger events. The number of things is small, and so
yeah,
it might be self-exciting in this classical extent only if the function is sort of as clustering. If you want to explain cluster. So, but if you take strange functions which try to space things.
Honestly, I didn't think very much on the name.
On the name.
It's just
no, it's because you have a.
Because it depends on itself.
So it comes from the external excitation, it comes from the constant excitation.
Yeah.
A lambda, a constant lambda.
Yeah.
And the lambda which comes from the class.
Yeah, that's why I call it self-exciting. Yeah.
But the interpretation in terms of this triggering that in clusters, that if you take a function of your y, you try to space things and you the number of points is very small in an interval, then you do something that has been big, you do nothing.
Yeah. So call it self-dependent intensity.
Okay.
That's only what I mean.
You might create a repulsion if you want, right?
Maybe. I don't know.
Self-excited may mean also negative excitation. So to do what you want.
Yes, you can. Yes, you can have one, and then you can go down below the one. Yeah, probably. But anyway, it's just my question is just about you have a lambda which depends on the whole path of y up to time t excluded. That's all. So this is the cluster representation, which dates back to 1974 of Oaks and Oaks. So you have an initial event with its replicas, and this one generates some replicas, and this one generates some replicas, and this one I didn't draw it, but this one will generate some replicas, and so on and so forth. This is one way to simulate the Poisson-Hooke's process. And the usual form of the intensity, which is considered in the literature, is, as François said, some constant plus this sort of convolution between the function phi, which is deterministic, and y, which is the process under consideration. So if you develop everything, that means that you have a sum of k of phi t minus tk of y for all the jumps of y which are before time t. Okay, but you can imagine some other form of intensity. It's not restricted to that. So here the existence condition is that the integral of phi is strictly less than 1. Otherwise, you will have an explosion of a number of objects.
Just a question: the function phi is a positive?
Yeah, sure, of course.
Because you have an alpha, so because you have an alpha, it might be a negative also.
Yeah. But no, here phi is positive. Actually, I must be sure, this is another question, I must be sure that lambda of y and t is positive.
Take negative and the positive part of it. So
of course. So, Bremo and Massoulier in 1996 constructed the Hooke's process with a capital phi in front of the same thing, and phi has to be also non-negative and Lipschitz continuous for the things to be well defined. Okay, so that's what I'm not finished. So what is the construction of Bremo and Massoulier? It is a construction which is based on a Poisson measure. That means the Poisson measure, here you have, if lambda of y and t is given by 1 plus, so I choose this particular form of phi, which is exponential minus 3/2 times x. So lambda of y and t is 1 plus this quantity. So you start with 0, and as long as you don't have a jump of y, you see that lambda y of t is equal to 1. So that means that the first jump of y will be in an exponential of parameter y. So one way to do this is to take you take the line here, and you first consider a marked point process of intensity 1, and mark which are uniformly distributed at 0, 1. And the first time you have a mark which is below 1, you say, okay, this is the jump of 1. But now when you have, when t is greater than t1, what happens? The lambda y of t is 1 plus exponential minus 3/2 t minus t1. So this is this quantity in blue. So it's bounded by 2, so you are considering a Markov process of intensity 2. So the jumps are the interval between the jumps is an exponential of parameter 2, and the marks are uniformly distributed over 0, 2. And the first time you have a point, but it is above the blue curve, so you don't count it. And here, the first time you have a point which is below the blue curve, you say it's T2 of y. So now, when you are greater than T2, the lambda y of t is 1 plus exponential minus 3 over 2 t minus t1 plus exponential minus 3 over 2 t minus t2. So it's bounded by 3. So you draw again a Markov process of intensity 3 and marks uniformly distributed over 0, 3. And the first time you have a point where the mark is below the orange curve, you say it's T3 of 1. And then you continue like this as long as you want, up to time, to the horizon time where you want to stop your simulation.
That's something I did not understand. Why did you discard the second point?
This one now?
Yes.
Because it's above the blue curve. Because it's the construction who gives you that. It's a construction. It's a theorem which says that you have to keep only the points which are below the curve at each time. It's the theorem of Remo and Massu. It's a construction. It's obtained by the thinning of the Poisson measure. Okay, so actually we went for in a completely different way of thinking. Consider of n, which is a Poisson process of intensity 1, and pi is its distribution. And you take y dot, which is predictable. So predictable means that it depends on at time t, it depends of all the past of n strictly before time t. And you assume that it is positive. And you consider its first integral, and you consider its inverse. So at the beginning, I was using this inverse. In the end, it turns out that it is the y minus 1. But at the very beginning of my computation, I choose y star, and I kept y star. So y star is y star. So what is it? If you have a curve like yt here, in green you have the first bisector, and y star of t is the symmetric of the blue curve with respect to the first bisector. Okay, so what are we doing with that? The first remark is that y star of n and t is the stopping time with respect to the filtration generated by n. And this is mathematically very important. Okay, so now I will consider I have capital N, or I don't know, fracture N, gothic N, is a set of all realization of a sample path. So the set of all sequence of points which are strictly less one, which are ordered and goes to infinity. This is this kind of space. So you have a sequence of time, and then you make you make a map which to a sequence of time gives you another sequence of time. You change the time in n. So the first interpretation is that your process y is kth jump is y of n and tk of n when you apply the map y to the kth jump of n. Okay, this is the first interpretation. So it seems simple, but sometimes it's misleading as a theorem. There is, in the book of Delachery and Meyer, who were not the first probabilists, there is a line which says the time change operation seems easy, but conceals many traps. So you have to be very, very careful with this little operation. You see, there is one problem here for those who knows. N has its own filtration, its own history. And now you have changed time in N. So that means Y of T is not adapted to the history of N. It's adapted to another history, which is the history, which is the filtration of N stopped at Y star. So we'll come to that later, but this is the main difficulty of this stuff.
Sorry, yeah, so your Y was a random process also.
Y is just a map from N.
Small one.
Small one is just a map,
yes,
from Gothic N to R plus. It's a process which takes a point process, yes, and gives you an increasing function. Continuous, strictly increasing function. That's all what it is. And it's predictable. That's the only idea. It's a time change. And it's a stopping time. Y star is a stopping time. Okay, so no.
It is stochastic.
It's deterministic as a function of a point process.
On the counting measure, it's deterministic.
Yeah,
right.
Yeah.
So, right.
Yeah, but then the counting measure will be randomized.
And then yeah, we create something which
it's
is
a deterministic map from N to a set of processes which are predictable. Okay. So another interpretation is the following. Imagine you are on a road and you have road signs. Okay. This represents the time jumps, in fact. And you have Alice, which drives at reference speed. And then she sees the road signs at the time tk of n. So that the process n actually jumps when Alice sees the road sign. And then you have Bob. Bob, he has his own clock, and it's not, they are not synchronized. The two clocks are not synchronized. But Alice knows the clock of Bob, but Bob doesn't know the clock of Alice, and he has his clock. He said he can say, okay, I've been driving for 1 hour, I've been driving for 20 minutes. He can do this, but it's not the same. His watch is not synchronized with the watch of Alice. But they see the same size in the same order, and at the end of the road, they have seen all of them, both of them. That's the interpretation, another interpretation of what is a time change. So if you look at what is called the history generated by Y, it's Y of t, it's what is known before time t when you observe Y only. It's exactly the Bob's information at his time t. He knows only that. But from the Alice's point of view, times t for Bob is time Y star n of t for Alice. So Alice, she knows the clock of Bob. So she knows Y star n of s. She knows the whole story of the Bob's clock. Okay. And well, what does she know? She then knows she knows exactly which road signs Bob saw before his time t and before her time Y star n of t. Because it's exactly this. So what kind of information Alice has more than Bob? Well, Alice knows n y star of t, Bob knows y of t, and the difference between the two is the history generated by, you have to know the clock of Bob. So this is the information which Bob doesn't have. It is the link between his clock and her clock. Okay. And now you have Charlie. Bob knows Charlie clock, but clock doesn't know Charlie's. No, it's contrary. Bob knows Charlie clock, but Charlie doesn't know, has no clue on his clock relative to Bob's. Okay, and now, of course, Alice knows everything. So that means that from what does C, what Alice knows from Charlie, it's the map, the composition of the map Z and Y. And if you look well, if you make the computation, it's very easy. You see from the point of view of Alice, Z composed with Y is exactly as the composition of N at time Y star of N, but Z star here is taken along the map of Bob and not on the map of Alice, on the path on Bob and not on the path of Alice. So just write down the equation and you get this thing. That means that if you want Z composed with Y equal to the identity, you must have this quantity Y star N of Z of star to be equal to T. And that means that Z star YT is equal to YNT, or C star YT is equal to Y star NT. So that's one reason to not put here -1. It's because the star here means that you take the inverse of Z, but for when the path is fixed. And now we will have something when we take the inverse, but when you see here you have path Y and here you have path N. So that's why it would be confusing in my mind to the real thing is that Z is 1 minus 1. -1 should be reserved to Z or to Y, but not to Y star. So this is the key point of what follows. And you have a first theorem, which is that f Y is left invertible if and only if the filtration, the history of Bob coincides with the history of Alice's point of view. That means that if Y is left invertible, that means Bob can retrieve the clock of Alice. What it means. And the next theorem is even better. Y is right invertible if and only if there exists a process Z which satisfies Z of t is equal N of Y of Z of t. And you have more than that, you have Y of Z of t less than S is in the filtration generated by Z up to time S. So if you recall what I said, the question I said before, question 2 was, no, I skipped question 2, I guess. No, it was before, no, back. Yeah, question 2 was, can we construct Y such that we have this equation solved? So this is Y, this is a Y, okay? And so we have solved, we have one step, we have done one step further. That means that if we want to construct a Hawkes process with respect to little y, we have to show that capital Y is right invertible. So it's a change of point. you have to solve a fixed point equation in some sense.
So, self-exciting is linear?
No hypothesis besides y is the only hypothesis I have is y dot is strictly positive and predictable.
So it does not rely on this particular representation.
No.
Short noise.
No.
So it's
No.
completely general.
Yeah.
So what's the definition of self-exciting?
Just that it has this form. But it solves something like this. Because when you have this, that means that the compensator of C is YZT. So its compensator depends on itself.
Deterministic function of the past and of the time.
Yeah, that's predictable. Okay. And the proof is simple. If there exists Z such that Y composed with Z is equal to identity, that means there exists Z star and capital Z, such that Z of T is N of Z star N of T. And you have the relationship I mentioned before, Z star N is equal to YC. And then you plug this identity in this, you get ZT is equal to N of YCT. Pardon?
This one Charlie is actually Alice, or like ABC?
Yeah, that means that Bob and Charlie can team up to retrieve everything. And then, if you look at the event y z of t is less than s, you rewrite like this, and you see that it depends on the filtration generated by z. So that was the second point. That means that yzt is a z stopping time. Okay, so it gives you a new simulation algorithm for a point for Hawkes process. Because if you look at this identity, what does that mean? That means that suppose that z exists. As long as you don't have a jump of z, this is y z of 0. Okay, so you have something like this. You have the y of the empty set of the empty configuration at time t1 of z must be equal to t1 of n. So you just have to solve numerically the equation y empty configuration x is equal to t1 of n. You simulate your Poisson point process. You look at the first time and you solve this equation, and it gives you t1 of c. Then you know what is the beginning, the first jump time of z, and you solve this equation. And more generally, tk of z depends on the k-1 first jump of z, and you have this equation to solve. And I try it. It's very easy to, when you use the usual expression of y, it's very easy to compute numerically the solution of these equations. That means that you don't have the algorithm of by thinning. As any thinning, you have some rejection, so you lose some point in your. You simulate too much point compared to what you will get in what you have in VA. Here you lose no point. Every point simulated in Poisson process has its image in the Hawkes process.
When you say simulate, you be the perfect sample of.
For a Poisson process starting at 0, I draw exponential 100 times.
Yeah, but here you want to. You say it's a simulation algorithm of the Hawkes process, right? Yeah. And so you depart from the point process and out of that you construct
T1 of 32.
And it stops because on this interval of Poisson point process.
It stops when you want when you stop to simulate your Poisson process. If you simulate 1,000 jump of your Poisson process, you get 1,000 jump of your Hawkes process.
Okay.
When you make the thinning with the Poisson measure, you simulate your Poisson process up to time t, and you have the Hawkes process up to time t. It's something which is dual point of view. Sometimes you have the Hawkes process on 0t, and here you have the first 1,000 jump of the Hawkes process. I don't know when they're.
But so if your initial point process is perfect in its points, then then the sample of this
is perfect.
Is perfect. One more question, because so I mean you still have to solve this equation.
Yeah, but numerically it's very simple.
And so you okay, so you know the function y, which is a map. It's a map of an infinite dimensional space built on counting measures, right?
No, if you sorry for the for those who are maybe I can. Démarrer la vidéo. Oh, sorry. Non. OK. Arrêtez la vidéo. So what? Qu'est-ce que je fais là? Ah. Oui, mais du coup, c'est pas moi qu'on voit. Ah, vous voyez. OK. If instance for if y dot of t is alpha plus beta exponential minus gamma t, say, that means that y of t is equal to so y of t is equal to alpha t plus integral from 0 to t beta exponential minus gamma s t minus s dys. You have this kind of thing. So that means that if when you start at time 0, at the very beginning, the first equation you have to solve is alpha. So I choose 1. I will explain that later, but I have to take 1 here. So it's t. So the first equation is T1 of y of z, sorry. Ty of z is equal to T1 of y. Okay, let's see that. The second equation is T2 of z plus beta exponential minus gamma T2 of z minus T1 of z is equal to T2 of a. So you solve this numerically, there is no problem at all. Just put the equation.
And simulate it in the stationary.
No, I have no idea how to do the stationary time. It starts from 0. Okay, because when you have Martingales, you have to have the origin of time. Martingales will start from minus infinity.
That's interesting.
Yeah, but for the time being, it was complicated enough to
and you can reach any,
as long as you can invert this thing.
And it's always like this, that if you know by induction, you compute the next point, it's always for this type of function.
Yeah. That's the interest of being predictable. Because you know that the whole thing here, which depends only on the previous jumps between before the one you are computing. Alors qu'est-ce qu'il faut que je fasse là maintenant? Oui, mais du coup, je ne vois plus. Affichage. Alors, pourquoi le partage d'écran devient en pause quand je fais ça? Non, c'est bon. OK. You have... ça ne marche pas? Ben ouais, mais je ne comprends pas pourquoi. Alors, repartageons. Ça partage. C'est bon? OK. For the corollary of that is you have a Martingale representation theorem for Hawkes process, given that they exist, of course. Huh? But if you have a function which is square integrable with respect to z, there exists a unique v which is z predictable such that you have this identity. So it's given as a trivial consequence of because if y is right invertible, then z is in fact left invertible. So you have the identity of the two filtrations, and that's enough to have you use the fact that for the point process, for the Poisson point process, you have this theorem, and it yields the theorem for the Hawkes process. So okay. So where does the question is, given y, does there exist an Hawkes process such that z of t is y and y of z of t? So I proved nothing for up to now. I just said if it exists, it's just satisfied. So the original motivation was the following: on the Wiener space, that means on the space of continuous function equipped with a Wiener measure, that means that B is a Brownian motion. There is an old idea from Föllmer, which has been reworked by Üstünel-Zakai in around 2010, which is you take the path, you take you take the function which are continuous from 0, 1 into R into itself to the path, you associate a new path, which is b of t minus integral from 0 to t of u dot ds. You just put a drift to the Brownian motion. And you have another toy, which is called stochastic differential equation, which is a very simple example of a stochastic differential equation, which is xt is b of t plus the integral of 0 to t of u dot xs. And the remark is the following: if this equation is equivalent to this equation, okay, I just put the integral term on the other side of the sign equal. And then if you look at this identity and this identity, that means that x of t is the solution of the equation u of x of t equal b. That means if you look at x not as a process, but as a map which to b associate the solution of this equation, you have two maps which are inverse from each other. That means that solving an SDE is inverting a map. So as we want to inverse something, maybe it's the same thing as it's the analog as solving an SDE. But when you solve an SDE, you know that you have many notions of solution. You have weak solution, you have strong solution, you have Martingale solution, and so on and so forth. So it's very, and you have a criterion from Üstünel, which says that you have an entropic criterion, but U, the map before, is invertible if and only if you have this kind of thing. So this is the entropy of the image measure by U of the linear measure mu. So it should be equal to that. I will go back to that later. And you have two approaches. Actually, we want to solve, to inverse a map. Okay. So first question is, can we mimic the SD's approach? And do we have an entropic criterion? The answers are both yes. So that means it leads us to refine the definition of what is a Hawkes problem. So given n a Poisson process and y a deterministic map from the set of point process to set of processes. You have a strong Hawkes solution to the Hawkes problem if there exists on the probability space where n and y are defined a process z such that zt is equal to nyzt. This is the first definition. The second definition is given y, can we construct another probability space such and with z with a z on it such that one holds. You have another problem which is given y, can we construct another probability space, another filtration, another y, such that this process y of stuff, y of, okay, you have many y, minus t is a local Martingale. That means is this process a Poisson point process of intensity 1? Okay. And exactly as in the case of Brownian SDs, there exists a solution to the weak problem if only there exists a solution to the Martingale problem. This is rather easy to show. You have a notion of strong uniqueness, which says that if x1 or x2 are two solutions defined on the same probability space, so they are a solution of a strong problem, then x1 is equal to x2. And you have the Yamada-Watanabe theorem. That means that if you have weak existence with strong uniqueness, you have strong solution. I like this theorem. Actually, it is not really a surprise because when you look at the proof, which is rather intricate for the Brownian case, the crucial step is the fact that the Brownian motion has independent increments. And this is a property which is shared by the Poisson process. So this is not really a surprise when you have defined the things in the proper way. Okay. So you can retrieve the result of Hawkes and Hawkes, Massoulier and Bremo. But now you have a strong solution to the Hawkes problem. Not as they use either the cluster representation or the filling of a Poisson measure. That means that they construct another probability space on which they construct Z. Here we are given n, we are given y, and we construct the Hawkes process on this space. And you have exactly the same theorem as you have in Massoulier-Bremo. And what are the meaning of the two hypotheses? This one means that you have sufficiently. Yes, this one means that you have sufficiently integrability for y dot. And this one, we assume that this function is Lipschitz. This is to ensure that you have strong uniqueness. So the only thing you have to show is that you have weak existence. And weak existence relies on the Girsanov theorem. So it's very strange because the Girsanov theorem is very well known in the Brownian case, but I never found a reference for the Poisson case. Imagine you have pi, which is the law of a Poisson process of intensity 1. You take nu, which is equivalent to pi. Then you know by Jacob and Bremo that there exists a y dot strictly positive such that the nu is absolutely continuous with respect to pi, and the density is lambda y. And if you set y of t is n of y star of nt, then you can prove that y under the new probability nu, under the filtration n y star, is a unique Poisson process. So it's a little bit more difficult than the Girsanov theorem for Brownian motion because you have this change. You have to take care of the fact that you change the filtration, and it's not complicates the things, the computation. So what is the weak existence? The Girsanov theorem says that y is a lambda y p Poisson process. And since y is equal to n of y of n of star t, you see that n lambda pi lambda y p solves the Martingale-Hawkes problem. And since we saw that when you solve the Martingale-Hawkes process problem, you solve the weak Hawkes problem, you have a weak solution. Okay, and the weak Hawkes problem. Okay. I will skip this kind of thing. So when you have a measure, you have a probability associated to a random variable Ln. You have a transformation of n, and you phi diaresis pi is hashtag pi is the law of phi of n. You have another way to modify the probability. You take pi, you take a non-negative function, and you consider the function, the probability, which has density lambda. And the entropy of phi hashtag pi relative to pi is the expectation of lambda log lambda if lambda is the density of the phi pi with respect to pi. Okay, and the entropy criterion is the same. The map Y is left invertible if and only if the entropy of y star p, y hashtag p relative to pi, sorry, is the expectation of this quantity, with this quantity is m of x, 1 plus x log of 1 plus x minus x, so it's this function. This is a function which appears here and there in the theory of Poisson process. In several papers, it appears. So it's the equivalent of x squared over 2 for the Brownian motion. So it has very good properties because it's strictly convex, positive, and so on and so forth. So it's a kind of divergence of F divergence. Okay, the corollary is that the entropy of the image of pi by Z satisfies this equation. So you have another, you can compute the entropy of the image measure of your Hawkes process. Okay, and then you have a bonus, which is a variational representation of entropy. This is a problem which has been largely investigated for the Brownian motion. There is one paper by someone who is called Zhang, I think, who solved it for the Poisson process, but once more, he started from the Poisson process on the line, and then he embedded in a Poisson measure, and then solved the problem in the Poisson measure, and then he went back to the line. So here we don't need this. You have something which is totally intrinsic. So what is P plus of M? It's a set of process which are positive and such that this integral is finite. Since I have a minus something, is something. If this thing is infinite, I will have some problem. Okay. And the work in progress are the following. I guess, I am almost sure that, you know, everything we did until now requires that y dot is positive. Okay, but there are some works on the literature on Hawkes process when they want to have intensity which vanish. So it's not yet, it cannot be done as we want by this method, but I guess that if you find, if you have y dot, you can add epsilon to y dot, it becomes strictly positive because y dot has to be non-negative. So if you add epsilon, it's become non-strictly positive. And then if you can go to the limit here, then you can go to the limit there. And I expect that in the end, you will get a limit of the y epsilon pi, which will give you the law of the process with maybe with possibly null intensity, sometimes null intensity. Okay. There are some other work. My PhD students are working on that. If you start with an infinite number of Poisson point process, and you may construct some transformation which are still adapted, but which mix all the coordinates. If everything works well, and I guess so, you may construct an infinite number of Hawkes processes which are self-exciting. The problem I mentioned in the beginning for neurons. And the last point is if you take a mark point process, that is a Poisson process, and then you have marks which are distributed according to a probability measure. If we can do the same thing, the same procedure, that we will be able to construct self-excited Levy processes. And I know there are some people who are working on that. So I hope so. I hope it will work, but I don't see any obstacle to the development of the stuff. Okay, that's all.
Thank you. Any question on the bridge? No?
Yeah.
So, in your last slide, not this one, the one before. So your construction, if I got it correctly, was for one point process. But if you take a vector, not necessarily dimensional, because set point, then it's the same construction holds.
Yeah.
So then if you have a closed network.
Yeah. Yeah. I don't think it will be very different, but the case where n or a subset of n, I don't think it will be very different because you will consider compact subsets of R plus time n. So each time you will have a finite number of coordinates which are active at the very moment. Because if you want to define a measure, a point measure on R plus times n, what you do is you define the measure on each compact of this space. So each time you have a finite number of components which are active.
And so second question. So I mean, this entropy characterization. So if you take one case where one knows about the existence, and can one use that also to check the, or let me put it differently, can one use that to prove that computationally that some processes are not invertible, right? Or to define, to show an example where
I know I have no example. No, I think where it's useful, it's in the criterion of here in the variational representation. And what you are doing is that you are using that for simple y, that means y's which are stepwise. You can compute everything, and then you pass to the limit. That's useful for that. That means that you start for a simple y, where you know that you have equality, and then you pass to the limit. But if you start, I didn't really try, but I don't think it's for if you want to reprove the theorem of Bremo and Massoulier by the Entropic criterion. I'm not sure it's very feasible, except by approximating the y by something simpler and best pass to the limit. But no, it's a very nice criterion. The thing is to find some application. The application are pass to the maybe that's why I think it's a good tool to construct Hawkes process where y dot may vanish.
And so perhaps the last question.
Oh, yeah.
Point. So we had a talk by Yamada-Watanabe a couple of weeks ago on perfect simulation.
Yeah.
This kind of decomposition.
I was wondering, so it's also, I mean, she does this for the vector thing, right?
Yeah.
And she does a copying from the past.
Yeah, but I have no past here because I start at 0.
Yeah, but
it's I still have to do the stationary situation where,
no, it's not a copy from the past for the stationary, but she uses a copy from the past.
Yeah.
So she looks at she builds the state at time t by adding past from time t up to, and she shows that and she shows that you can construct things by adding a finite horizon of past, and they call this in neuron in this neuron Kalikov decomposition, basic inequality.
okay.
Their aim is to build as yours a perfect sample of the state at time t. And so if you try to go backward, you have all these point processes, and you have this, like in Remo, you have these consistency things.
Yeah.
And she shows it is possible if the parameter
Satisfied. Yeah. Okay.
And then you can, and so this is, I have heard of that in many kind of things. So perhaps it improves on what.
Yeah, probably.
What you do improves on what the state of it, because they have conditions to build this perfect sample. They need the intensity function to be bounded by a constant.
Oh, okay.
And it's a big problem in this approach
because it's not really realistic.
Because it's not realistic, and so perhaps
yeah.
Circumvent this.
Yeah.
She sent references.
Yeah, sure. But we have to. This is almost done, but we have. I'm waiting for my co-author to give the green light before submission. It's not finished. Yeah, François.
Yeah, I have a question because since all your constructions are starting from the 0.
Yeah. 0 condition. Yeah.
0 condition at 0.
Yeah.
Why do you need an existence condition? I mean, if you start at 0, it should always.
No. You may have explosion.
Infinite time?
Yeah. If you look at the expectation, if you look at the expectation of your Hawkes process at time t, you have an equation which is the expectation of z of t is equal to something plus the integral of phi times the e of z of t. Yeah. And so if this is greater than 1.
In expectation, but
yeah, but it's likely that if you have a process with no expectation, it won't be a very nice problem. Okay, you have Hawkes.
So at least you could construct it up to the explosion time.
Yeah, probably. Yeah, but I didn't. I want here. I need to have no explosion time. I want. Maybe we can refine the proof to have the exclusion.
So what you mean by existence is existence
up to infinite time. 0 infinite.
Other questions?